Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS Group. In this video, I will discuss about inverse Laplace transform. Inverse Laplace transform. Okay. So the definition of inverse Laplace transform is if L of Ft equal to Fs, then we say the function Ft is inverse Laplace transform of Fs, and we write L inverse of Fs equal to Ft. Okay. For example, we know that L of e to the power 3t is equal to 1 by s minus 3. So Laplace transform of e to the power 3t is 1 by s minus 3. So Laplace inverse Laplace transform of 1 by s minus 3 will be e to the power 3t. Okay. Now in my previous video I have discussed about Laplace transformation, and we already know all the basic Laplace transform of the basic functions. So here I will write the basic inverse Laplace transforms result of some basic function. So number 1, L of 1, we know that L of 1 is 1 by s. So L inverse of 1 by s will be 1. Number 2, L inverse of 1 by s square equal to t. Number 3, L inverse of 1 by s to the power n plus 1 will be t to the power n by n factorial. Number 4, L inverse of 1 by s minus n equal to e to the power at. Number 5, L inverse of 1 by s square plus s square equal to sin at by a. Number 6, L inverse of s by s square plus s square equal to cos at. And number 7, L inverse of a by s square minus s square will be sin hyperbolic at by a. Number 8, L inverse of s by s square minus s square will be cos hyperbolic at. Okay, so these are the basic inverse Laplace transforms of some basic functions. Okay. Now we'll go to some basic properties of inverse Laplace transform. So before that, let me remove this. So first property is linear property of inverse Laplace transform. Linear property of inverse Laplace transform. This property states that if L of f1t equal to f1s and L of f2t equal to f2s, then L inverse of c1 f1s plus c2 f2s will be c1 f1t plus c2 f2t. Okay, so where C1 and C2 are arbitrary constant. The proof is very simple. Since L of F1t equal to F1s and L of F2t equal to F2s, therefore F1t equal to L inverse of F1s and F2t equal to L inverse of F2s. So by the linear property of Laplace transform, we know that L of C1 F1t plus C2 F2t equal to C1L of F1t plus C2L of F2t, which is equal to C1 F1s plus C2 F2s. Then L inverse of C1 F1s plus C2 F2s will be equal to C1 F1t plus C2 F2t. Hence our proof. Okay. Now I will go to the next property, which is called first shifting property of inverse Laplace transform. First shifting property. So this theorem states that if L inverse of, not if, L inverse of f of s minus a equal to e to the power at, L inverse of fs. Okay. Let us take an example. Suppose we have to find inverse Laplace transform of 6 into s minus 4 by s square minus 4s plus 20. Okay. So here the denominator can be written as s minus 2 whole square, that is s square minus 4s plus 4 and plus 4 square. Okay. And the numerator can be written as 6 into s minus 2 and it will be minus 12, and so we have to add minus 12. Okay. So 6 into s minus 2 this will be minus 24. Okay, this will not be a bracket, 6s minus 4. So minus 12 plus 8, this will be minus 4. Okay. Now this can be written as 6 into s minus 2 by s minus 2 whole square plus 4 square plus L inverse of 8 by s minus 2 whole square plus 4 square. Okay. Now here you can see that here if instead of s minus 2 there is s, then this was s by s square plus 4 square, and that is the inverse Laplace of cos 4t. So since there is s minus a in place of s, we have to use first shifting property, and it will be e to the power 2t cos 4t, 6 is constant, plus 8 into, here we are multiplying dividing by 4, so it will be e to the power 2t sin 4t, that is 6 e to the power 2t cos 4t plus 2 e to the power 2t sin 4t. Okay. So this was the example of first shifting property. Okay. Now we'll go to second shifting property. second shifting property. So this property states that if L inverse of Fs equal to Ft, then L inverse of e to the power minus As Fs equal to f of t minus a when t greater than a, 0 when t less than a. Okay. Let us take an example of second shifting property. So we have to find L inverse of 8 e to the power minus 3s by a square plus 4. Okay. So we will do solve this sum using inverse Laplace transform. So L inverse of, we know that L inverse of 8 by a square plus 4 is equal to 8 into L inverse of 1 by a square plus 4, and we are multiplying and dividing by 2, so that it will be sine of 2t. Okay, that is 4 sine 2t. Now applying second shifting property, L inverse of 8 by a square plus 4 into e to the power minus 3s is equal to 4 sine 2 into t minus 3 when t greater than 3 and 0 when t less than 3. So L inverse of 8 into e to the power minus 3s by a square plus 4 is equal to 4 into sine 2t minus 6 when t greater than 3, 0 when t less than 3. Okay. So this was an example of second shifting property. Okay, now we will go to the next property called change of scale property. Change of scale property. The statement of this property is if L inverse of Fs equal to Ft, then L inverse of Fas equal to 1 by a f of t by a, where a is a constant. Okay, so let's take an example of change of scale property. So let us find L inverse of 3s by 4 square plus 16. Okay, so we have L inverse of s by a square plus 4 square is cos 40, you know this. Now by change of scale property, L inverse of 2s by 2s whole square plus 4 square equal to 1 by 2 cos 4 t by 2. Okay, now L inverse of 2s by 4 square plus 16 equal to half cos 2t, or 2 by 3 L inverse of 3s by 4 square plus 16 will be half cos 2t. Therefore, L inverse of 3s by 4 square plus 16 will be 3 by 4 cos 2t. So this was an example of change of scale property for inverse Laplace transform. Now I'll go to the next property, inverse Laplace transform of derivatives. Inverse Laplace transform of derivatives. So this theorem states that L inverse of f dash is equal to minus t L inverse of fs. Okay. So let us take an example. L inverse of s by s square plus 9 whole square. So we have L inverse of 1 by s square plus 9 is equal to sine 3t by 3. We know this. Now L inverse of d ds of 1 by s square plus 9 will be minus t L inverse of 1 by s square plus 9, that is minus t sine 3t by 3. So L inverse of minus 2s by s square plus 9 whole square is equal to minus t sine 3t by 3. So minus 2 L inverse of s by s square plus 9 whole square is equal to t sine 3t by 3. Therefore L inverse of s by s square plus 9 whole square equal to t sine 3t by 6. Okay. Now I'll go to the inverse Laplace transform of nth order derivative. Nth order derivative. Now I'll discuss about inverse Laplace transform of nth order derivatives. Nth order derivatives. Okay. So the statement is L inverse of f s nth order derivative equal to minus 1 whole to the power n minus 1 whole to the power n t to the power n f t. Okay. So let us take an example. Let's find L inverse of log of s plus 3 by s plus 2. Okay. So let fs equal to log of s plus 3 by s plus 2, which is equal to log of s plus 3 minus log of s plus 2. Now f dashed s will be equal to 1 by s plus 3 minus 1 by s plus 2. So L inverse of f dashed s equal to L inverse of 1 by s plus 3 minus L inverse of 1 by s plus 2, and that is equal to e to the power minus 3t minus e to the power minus 2t. Now minus t L inverse of fs equal to e to the power minus 3t minus e to the power minus 2t. So L inverse of fs equal to e to the power minus 2t minus e to the power minus 3t by t. Hence our result. Now I will go to the next property, inverse Laplace transform of a function multiplied by s to the power n. Inverse Laplace transform of a function multiplied by s to the power n. Okay. So this theorem states that if L inverse of fs equal to ft and f0 equal to 0, then L inverse of sfs equal to f dash t. So this was for multiplied by s to the power 1, and if it is multiplied by s to the power n, then L inverse of s to the power n fs will be fnt, that is nth order derivative of ft. Okay, and the condition should be f0 equal to f dash 0 equal to up to f of n minus 1 0 will be equal to 0. So let us take an example. Suppose we have to find L inverse of s by s plus 1 to the power 5. Okay. So we know that L inverse of 1 by s to the power 5 is equal to t to the power 4 by 4 factorial. Then L inverse of 1 by s plus 1 to the power 5 will be e to the power minus t into t to the power 4 by 4 factorial. And then by the above theorem, this function is multiplied by s plus 1 to the power 5, and this will be f dash t, that is ddt of e to the power minus t into t to the power 4 by 24. So this will be 1 by 24 into minus e to the power minus t into t to the power 4 plus 4 t cube e to the power minus t. Okay. Now I'll go for the next problem. If it is a square instead of s, then first we have to do this part, and then again we repeat this, that is L inverse of a square s plus 1 to the power 5 will be ddt of 1 by 24 to 4t cube e to the power minus t minus e to the power minus t to the power 4. Applying the first theorem, because this will be the second order derivative. So already we have done the first order derivative. Now this will be equal to 1 by 6 into 3t square e to the power minus t minus t cube e to the power minus t, and minus 1 by 24 into 4t cube e to the power minus t minus e to the power minus t 4 t to the power 4. So this is our required result. Now I will go for the next property. If the function is divided by s, then what will be the inverse Laplace transform of the function. So next property is inverse Laplace transform of a function divided by s. Okay. The theorem states that if L inverse of fs equal to ft, then L inverse of fs by s equal to 0 to t fu du. Okay. Now let us take an example. Suppose we have to find L inverse of 1 by a square into a square plus 1. Okay, applying this property. Okay, now we know that L inverse of 1 by a square plus 1 is sin t. So L inverse of 1 by s into a square plus 1 will be integration 0 to t sin u du, that will be minus of cos u 0 to t, that is minus cos t plus 1, 1 minus cos t. Again this function has been divided by s, that is a square into a square plus 1. So this will be integration 0 to t 1 minus cos u du, and this will be u minus sin u 0 to t, that is t minus sin t minus t. So okay, not minus t, if you put 0 it will be 0, so the result is t minus sin t. Okay, now I will go for the next example of this theorem. Let us take L inverse of 1 by s into log of s plus 3 by s plus 2. So let fs equal to log of s plus 3 by s plus 2. So L inverse of fs is equal to e to the power minus 2t minus e to the power minus 3t by t. We have done it before. So L inverse of 1 by s fs will be integration 0 to t fu du, that is 0 to t e to the power minus 2u minus e to the power minus 3u by u du. Now I will go to the you will do the remaining part. It is your home assignment. And now I will go to the next property, that is called inverse Laplace transform of integrals. Inverse Laplace transform of integrals. Okay. So this theorem states that if L inverse of fs equal to ft, then L inverse of s to infinity fu du equal to ft by t. Okay, let's prove this. The proof is very simple. Since L inverse of fs equal to ft, so L of ft equal to fs. Now we know from the previous chapter of Laplace transform, L of ft by t equal to s to infinity fu du. Therefore L inverse of s to infinity fu du will be ft by t. Okay, so now I'll show you some proofs of the theorems. Till now I have just only states the theorem and showed the example of those theorem. Now I will prove some theorems of the previous theorems, because those are very important. The proofs are very important. Okay. So proof of the second shifting property. The statement I am writing again of second shifting property. Second shifting property. If L inverse fs equal to ft, then L inverse of e to the power minus s fs equal to f of t minus a when t greater than a, 0 when t less than a. So since proof is, since L inverse of fs equal to ft, so L of ft equal to fs, let gt equal to f of t minus a when t greater than a, 0 when t less than a. Therefore by second shifting property, by second shifting property of Laplace transform, L of gt will be e to the power minus as fs, and therefore L inverse of e to the power minus as fs equal to gt, that is L inverse of e to the power minus as fs equal to f of t minus a when t greater than a, 0 when t less than a. So this was the proof of second shifting property. Now I'll go to a proof of change of scale property. Change of scale property. So the statement is, if L inverse of fs equal to ft, then L inverse of fs equal to 1 by a f of t by a. Now the proof is, since L inverse of fs equal to ft, so L of ft equal to fs. Now L of 1 by a f of t by a equal to 1 by a L of f of t by a. is equal to 1 by a 1 by a f of s by 1 by a by change of scale property of Laplace transform, and that is equal to f of s. Therefore L inverse of f s will be equal to 1 by a f of t by a. Okay. Now I will go to the proof of inverse Laplace transform of derivatives. Inverse Laplace transform of derivatives. So the statement is, for the first order derivative, L inverse of f dash s, L inverse of f dash is equal to minus t L inverse of fs. Okay. Now the proof is, let L inverse of fs equal to ft, therefore L of ft equal to fs, therefore L of t ft we know that is equal to minus dds of fs, that is equal to minus f dash s. Okay. So now minus L of tft equal to f dash s, that is L of minus tft is equal to f dash s. Therefore L inverse of f dash s equal to minus tft. So this was the proof of inverse Laplace transform of derivatives. Okay. Now I'll go to the proof of inverse Laplace transform multiplication by s to the power n. Multiplication by s to the power n, and the proof of the statement was L inverse of s fs will be equal to f dash t. I am showing here by taking n equal to 1. Okay. So since L inverse of fs equal to ft, therefore L of ft equal to fs, therefore L of f dash t equal to s fs. We know this from Laplace transform. This is equal to s fs since f of 0 equal to 0. It is given in the statement f0 equal to 0. Okay. Therefore L inverse of s fs will be equal to f dash t. Hence the proof. Okay. Now this was all for this video. I have discussed in this video the definition and basic properties and their proof and the corresponding examples of some important results of inverse Laplace transform. And you watch this video. If you have any query regarding this video, or if you face any problem during practicing the problems of inverse Laplace transform, you can contact with me. My contact details is given at the first slide of this video. Thank you.